in the previous videos we studied homomorphisms of groups, and we looked at when groups are isomorphic. So I'm going to do some exercises in this video to help understand these concepts, and so that you get comfortable working with homomorphisms. So as a problem, consider the following. So the problem asks to describe all group homomorphisms from the group of integers to itself. So in other words, we are interested in describing group homomorphisms from the group of integers under addition. Remember, always when I read Z, it's always under addition, to itself. So how do you do this? So let's look at what can possibly be a group homomorphism. So suppose that phi is a group homomorphism from the integers to integers. And if you recall from the properties of homomorphisms that we have already studied, we know, for example, that the identity element under a group homomorphism must map the identity element. In this case, the identity element is 0. So this is guaranteed, this is forced by a group homomorphism. But now suppose that phi of 1 is some integer. So phi of 1, remember, is some integer, so I am going to call it a. Okay. Then what is phi n for another integer n? So group homomorphism properties will tell us that phi of 1 plus 1 is equal to phi of 1 plus phi of 1, right? This is the definition of a group homomorphism. And what is phi of 1 plus 1? That is just phi of 2, because 1 plus 1 is 2. On the other hand, I have declared phi of 1 is a, so this is a plus a. What is a plus a? A is an integer, so this is just 2a. So phi of 2 is 2a. What is phi of 3? 3a. The same reasoning. So in general, phi of n is na if n is positive, right? Because phi of 1 is a, phi of 2 is 2a, phi of 3 is 3a, phi of 4 is a plus a plus a plus a, 4a, and so on. Now, what about negative integers? What is phi of minus 1? Again, another property of group homomorphisms that you recall from the previous video, phi of minus 1 must be minus of phi of 1. I am writing this in the additive notation here, what we learned earlier. What we wrote earlier was phi of A inverse is equal to phi of A inverse, right? That means the symbol is less important here. The concept is image of the inverse of A. A inverse is just a symbol for inverse of A. Image of the inverse of A is the inverse of the image of A. So in this case, inverse of 1 is minus 1. So minus 1 maps to inverse of the image of 1. So which was A. So phi of minus 1 is minus A. So that means phi of minus 2, by the same logic as before, is minus 2a. So you have phi of minus n is minus na. So for all integers now, not just positive integers, for all integers n, we have phi of n is na, right? So let's take a minute to think about what this means. I have only prescribed what is phi of 1, right? And I called it a. It's some integer, I called it a. But then I have no choice on what the other images should be. Once I determine what phi of 1 is, I am forced to have phi of n equals na. So how do you express this phenomenon? So what we can write is phi is determined by phi of 1. which is to say that once you fix phi of 1 or once you give it a name small a, every other image of phi is determined, because once phi of 1 is a, phi of n is na. So phi is determined by phi of 1. All you need to specify, in other words, all you need to specify to give a group homomorphism from Z to Z, we only need to define what should be the image of 1, right? Because if I define what image of 1 is, a homomorphism will have to be fixed once you determine what phi of 1 is, because once you define phi of 1, phi of n is automatically defined. This is the power of a group homomorphism. Once you define what phi of 1 is, all other images, all the other infinitely many integers images are determined. Now the next question is, what are the possible choices for phi of 1? So first point is this, that to give a homomorphism from Z to Z, we only need to define phi of 1. We don't need to sit down and say what is phi of 1, what is phi of 2, what is phi of 3, what is phi of minus 1. We don't need to do that. We only need to say what is phi of 1. Others will follow automatically from the definition of a group homomorphism. So now all we need to do is define phi of 1. But what can be phi of 1? Can phi of 1 be any integer? It can be any integers, because in the calculation that we discussed earlier, a was an integer. I can put a to be any integer. I have a valid homomorphism after I define phi of 1 to be a. So for any integer a, define a group homomorphism phi from Z to Z by setting phi of 1 to be a. Once you set phi of 1 to be a, as I have already noted, every other phi n is determined, and give me any integer a, I can put phi of 1 equals a, right? So then phi is a homomorphism. This is what I am claiming. This is the exercise that we have done. I can, no matter what a is, I can declare phi of 1 to be a, and once phi of 1 is a, phi of n will automatically be na, right? So for any n. So this is the homomorphism that is determined by a. So to answer the original question, remember what was the original question? Describe all group homomorphisms from Z to Z, and we have done that. So what are the group homomorphisms from Z to Z? The group homomorphisms are determined by phi of 1 by, let's say, the image of 1, and image of 1 can be any integer. So this is the answer to the question. The group homomorphisms from Z to Z are determined by the image of 1, and the image of 1 can be any integer. So you have group homomorphisms from Z to Z are determined by integers again. So they are determined by Z again. That is the solution to this problem. So now I will ask you a question to continue this problem. Which of these homomorphisms are isomorphisms. Recall that isomorphisms are group homomorphisms that are bijective set functions. Okay, so which of these homomorphisms are bijections is what I am asking now. So I am going to use the letter A as a subscript to denote that phi of A sends 1 to A. So phi of A is the homomorphism from Z to Z sending 1 to A. And the previous problem we have solved by saying that all group homomorphisms of Z to itself are of the form phi of A. So which of these are bijections? So for example, if you take A to be 2, what is phi 2 from Z to Z? It sends 1 to 2 and so on, right? It sends, just I will write it for clarity for you. Where does it send it to? It will send it to 4 because phi of 2 must be phi of 1 plus 1 and so on. So phi of n in general, so I will write that here, phi of n in general simply 2n. Is this a bijection? Think about for a minute. Recall that bijections are 1 1 and onto. Bijections are injective and surjective. Those were the words I used, I introduced in a previous video. Is it 1 1? It is 1 1 but not onto. That is because it's not onto because one is not in the image of clearly, right? Because phi 2 sends an integer n to the integer twice n, 2n. Is there any integer such that 2n equals 1? There is not, because no integer multiplied by 2 equals 1. So 1 is not in the image. So phi 2 is not onto. So similarly, phi A is not onto for A greater than or equal to 2, right? Because for the same reason, phi A sends n to A n, and if A is greater than or equal to 2, A n cannot equal 1 for any n, right? So it sends an integer to A times this. If A is at least 2, it cannot equal 1, so it is not onto. What about A less than or equal to minus 2? For the same reason, it is not onto for A less than or equal to minus 2, right? Because again, minus 2A can never be equal to, minus 2n can never be equal to 1, minus 3n can never be equal to 1. On the other hand, phi 1 is simply the identity map, right? Because phi 1 of n is n, so it is bijective and it is an isomorphism. What about phi minus 1? Phi minus 1 sends n to minus n, and this already we know is a homomorphism, and you can clearly check that this is also an isomorphism. Because every integer is in the image, it's onto. Because is 10 in the image? Yes, because minus 10 maps to 10. Is 100 in the image? Yes, minus 100 maps to 100. Is it 1 1? It is certainly 1 1. All phi A's are 1 1. Okay, that we have discussed. Kernel of phi A is 0. So it is an isomorphism. What about phi 0? So we have addressed all integers greater than or equal to 2, less than or equal to -2, and 1 and -1. What about phi 0? Phi 0 of n is just 0. So phi 0 is the 0 map, which is to say phi 0 sends everything to, so that is every integer to 0. So certainly phi 0 is not an isomorphism, right, because it is not onto and it is not 1 1. So we have determined that only two of these phi s are isomorphisms, phi 1 and phi -1. So now let me summarize the whole problem as follows. Every group homomorphism from Z to Z is one of the So this is the answer to the original problem. Determine all group homomorphisms from Z to Z. They are of the form phi A as A varies in Z. These are all the homomorphisms. So phi A as A belongs to Z is the set of all homomorphisms. Phi A is an isomorphism if and only if A is 1 or A equal to -1. This is the second problem that we did, right? It's an isomorphism only if A is 1 or -1. Phi A is injective if and only if A is not 0. This I didn't explicitly say, but it's an exercise for you. It is the reason that phi 2 was not an isomorphism was that it's not on 2. It is 1 1, because if what does phi 2 do? Phi 2 sends n to 2n. If 2n is 0, we have already discussed in an earlier video that a group homomorphism is injective if and only if the kernel is 0, the trivial subgroup. If 2n is 0, then n must be 0. So kernel is 0. And phi A is surjective when is it surjective? If and only if A is 1 or A is -1. Remember that for any other integer it's not surjective. So the summary of these problems, which you should carefully understand, this is an important example of group homomorphisms and the properties that we learned about group homomorphisms, and this description is hopefully giving you a clearer understanding of all group homomorphisms from Z to Z. Okay, so let me do one more problem, and I will do the solution also, so that you understand how to apply the notions of group homomorphisms that we learned. So let G be a group. So this is the second problem of this video. Let G be a group and let A be an element of G. Let G be a group, let A be an element of G. Suppose that order of A is R. So what is order of A? I am going to recall it here. Order of A is the smallest positive integer n, let's say D, such that AD is identity element. This was our original definition of order. It is the smallest positive integer such that A power that is identity element. Here I am saying that order of A is some integer R. So obviously it's a positive integer. In other words, I am saying that some power of A is identity, some positive power. And now suppose that a power n is also identity for some other positive integer. N, then show that R divides n. So this is the problem. Okay, so the problem is saying that if order is given to be a number R and a power n is identity for some other number n, all positive numbers, then R must divide n. Okay, what is the solution of this? I am going to recall for you another description of the order that I gave after I defined homomorphisms. Consider the homomorphism from Z to G which sends some integer m to a power m. In an earlier video already we saw that phi is a group homomorphism. Phi is a group homomorphism that we already saw in a previous video. We also saw that if you consider the kernel, so kernel of phi is Rz, where R is the smallest positive integer such that a power R is identity. Remember, in general there is another possibility. Kernel of phi may be either Rz or kernel of phi is 0. This is also possible in general because there may not be any kernel of this map. That means a power m may never be identity for any positive integer. Okay, so this is a possibility in general, but in our problem kernel phi is not 0. I should really put as a set, because kernel phi is a 0 is a possibility in general, but in our problem it's not possible, because in our problem remember we are given that order of A is R, where R is a positive integer. Order has to be either 0 or positive integer always, and we in this problem are given that order is a positive integer. So kernel phi is not 0 because R belongs to the kernel. So note that R is a positive integer, so kernel is non-zero, so that doesn't happen. So kernel is this is not going to be the case in our problem. So kernel is Rz. So in general kernel is generated by the order of A. Kernel is generated by the order of A. Okay, now let's look at the problem more carefully. So R is the order of A and a power n is equal to identity for some integer n. Since a power n is identity, we have that n belongs to kernel phi, right? Because what is phi? Phi sends m to a power m. So phi of n is a power n, which is identity. So n belongs to kernel phi, but kernel phi, as we discussed earlier, is Rz. So n belongs to Rz. What does this mean? Then n equals R times m for some m, right? Because remember, recall, what is Rz? RZ is the set of multiples of R. It's R, 2R, 3R, minus 2R, minus 3R and so on. If n belongs to them, n is of the form. So n is a multiple of R. So R divides n, which is exactly what the problem asked us to do. It asked us to do that R divides n, which is what we have shown. Okay. So the keep in mind that if element has order R and a power n is identity, then R must divide n. Basically what happens is that if you take A and you write multiples of A, sorry, not multiples, powers of A. Take A and write powers of A. So you have A power 0, which is identity. Then you have A squared, A cubed. There are two possibilities. Either you will never we never encounter E in this sequence, right? So it keeps going. So A power 100, A power 1000 and so on. So they are all distinct and E is never there. Clearly the group must be infinite in this for this case to occur. The other possibility is E occurs of course when I say E never occurs, E certainly occurs at the beginning. We never encounter E in this sequence after A power 0. A power 0 is E, so we do have E in this, but if the sequence actually starts with A, not with A power 0, in this sequence either E appears or E doesn't appear. If E doesn't appear, they are all distinct and the group in particular must be infinite. Or E occurs in this sequence and order of A is the first place where E occurs. Again, I am not considering this, so let me not even put that in the sequence. I keep looking at A squared, A cubed, A power 4, A power 5 and so on, and the first time I see E, if it's A power R, then R is the order of A. And the point is, the sequence then repeats. So suppose A power 5 is identity. So the sequence is A squared, A cubed, A power 4, A power 5, A, okay, which is E, as I said. I am assuming this. So example. And then what is A power 6? This is just A power 5 times A. So this is just A. So the sixth element is again A, then A squared, A cubed. This is same as A power 7. This is same as A power 8. A power 4 is A power 9. A5, A power 10, which is also again equal to A. So the sequence is just repetitions of this. So this block keeps repeating, this segment keeps repeating forever. So what we are saying is, if A power 100, A power some number is E, that number must be a multiple of 5. So this is E. So in this block, E must appear at the last spot in each block, and that spot is the multiples of 5. So this is the fifth position. Fifth position, this is the 10th position, this is the 15th position, this is the 20th position. Okay, so the problem is essentially encapsulating the data that we just discussed. If A power n is E, then it must be a multiple of the first time you encountered E in this sequence. And let me quickly illustrate both of these possibilities. Both of these possibilities occur For example, if you take z to be z and a to be 1, or let's say 3, just if you take 3, if this sequence, again remember in the general case we use the multiplicative notation a squared, a cubed, but when we are dealing with integers we use additive notation. So the sequence will be 3, 6, twice, right, 2 times 3, 9, 12, 15, 18 and so on. So we never encounter 0. This is the possibility number 1 here. So the sequence of this is a sequence of distinct integers never containing 0. So this is the first possibility. On the other hand, if you take G to be some other group, like for example, if you take Z to be the group of fourth roots of unity, fourth root of that we encountered before, and you take a to be I. So you start with I, then you take I squared, which is minus 1, then I cubed, which is minus I, but then once you come to I power 4, it is 1. So this is the segment that keeps repeating. So the next I to the 5th will be I again, I to the 6th will be minus 1, I to the 7th will be minus I, and I to the 8th will be 1 again. So this will be repeated. So the segment that keeps repeating is I, minus 1, minus I and 1. So then you repeat this and then you repeat this. You keep repeating this forever, and in particular we know that order of I is 4 because the 1 is appearing in the 4th spot, 8th spot, 12th spot, 16th spot and so on. So this illustrates for you the point of this exercise. Okay, so let me now end this problem by doing a related problem which exactly uses this, and this also makes use of the notion of a group homomorphism. So let's say G to G prime is a group homomorphism. And let's say I take an element in G. Suppose that the order of A is R. So I could have simply written this as an order of A is R. The problem is, what can you say about order of phi of A? So the problem is, if you have a group homomorphism and an element is fixed which has some finite order, what is the order of the image? Can you say anything about the order of the image? Order of A is R. What is the order of phi of A? How is it related to R, in other words? That's the question. So solution is the following. Let's recall that order of A equal to R implies A power R is identity. Now let me, this is identity of the group G, right? That is because A is inside R. Now let's apply phi to both sides. Right, so phi AR is equal to EG, so phi of AR is equal to phi of EG. Now continuing here and using the properties of group homomorphism, phi of AR is just phi of A whole power R. And what is phi of EG? That is EG prime, right? Because the identity element under a group homomorphism maps to the identity element. So phi of A whole power R is EG prime. By the previous problem, which I have written here, what is the previous problem? In any group, if A power n is E, then order of A divides n. So here phi of A power R is E power EG prime. So order of A, order of phi of A, whatever it is, divides R. That is all we can say. So what can you say about order of phi A? We can say that order of phi A divides R. So this gives you a restriction on the possible images of elements of a group under a group homomorphism. If an element has order 5, its image has to have an order that divides 5. So it has to be either 1 or 5. So in particular, if phi is a group homomorphism, let me shorten it like this, group homomorphism, and A is an element of G, has order 5, then phi of A has order 1 or 5, right? It's an immediate consequence of the problem, because whatever is order of phi A must divide 5. 5 being a prime number, it is either 1 or 5. So, and as a supplementary exercise, is a trivial exercise that I have repeatedly used. Let G be any group and let A be an element of G, then order of A is 1 if and only if A is E. Okay, so this is easy for you to do. Only element which has order 1 is E. Okay, so in coming back to this example, phi of A is order 1 or 5. So in other words, phi of A is either identity element or its order must be 5. So this is very useful to keep in mind. Order of an element must divide the order of the element. Order of phi of A must divide order of A. So I'll just recall for you what is R, or R is order of A. So order of phi A divides order of A. Okay. So let me stop the video here, and hopefully this gave you an idea of how to work with group homomorphisms and apply various properties that we have learned. So in the next video I will continue with my study of cosets that I have introduced, study of equivalence classes that I have introduced in a previous video. Thank you.